Okay, in this video we're going to talk about some MATLAB code that I use to compare a direct form 2 realization with cascaded second order sections of the same filter coefficients. Okay, so the difference here is we're going to implement a filter using fixed point math, and so there's a finite number of bits that we can use to represent each of the filter coefficients. And so we're going to have to quantize these filter coefficients to fit within a certain number of bits. Right? And so we want to compare the two different ways of implementing this type of filter. Okay, so the first thing we do is we just start with some filter that I just pull out of a hat. Okay, so in this particular case, if you choose n equal 4 on a bandpass filter, this is bandpass because of this notation, it's going to pass the frequencies in the range of 0.3 to 0.5 in normalized frequency. If you do that, you'll double a fourth order filter to get an overall eighth order filter. We'll eventually talk about this as another topic later in the course. Okay, so what you need to know is we have a filter. It's got the B coefficients, it's got the A coefficients, and we're going to quantize those coefficients. All right. So in a previous video we talked about how to do that. We're going to use that Q coefficient code that comes from the Proacus book. Okay. We're going to use B bits, where one bit is allocated for the sign of the number, and we have B minus 1 bits allocated to represent a combination of the integer part of the number and the decimal part of the number. Okay, so in this particular code I chose B equal 10, and that's the idea. I want you to be able to explore this. So whenever you do an assignment on this, you can choose different levels of precision to compare the filters or compare the implementations. Okay, in this next section, what I want to do here is I want to come up with the quantized coefficients for direct form 2. Okay, and I was looking at an example in the Proacus book, and it occurred to me that in some ways he doesn't give it a fair comparison, because notice here, look at the scale of the B vector. The first coefficient is 0.0018. Okay, and the largest coefficient is 0.0110. Compared to the A coefficient here, that's a lot bigger, 7.2589. Okay, so you're going to have to allocate some bits to the integer part of this number to represent the A's, and all those bits would be wasted on the B's because they're not in similar size. Okay, so one way you would fix that, and this is what you'd do in practice, is you'd scale the B vector before you quantize it, and then unscale it at the end. Okay, so scale it, quantize it, unscale it would be the steps. Okay, so that's what I'm doing here. I first of all take the B vector and divide by the max, and then multiply a max of B, then multiply by the max of A, and then we'll put the A's and B's on a similar scale. So I look at this, I've scaled the B vectors, and so these are the new B's. And what you want to notice here is that the maximum B is exactly the same as the maximum A. Alright, so clearly they're on the same scale at this point. Alright, so the next thing we do, we talked about this I'll change colors, this Q coefficient code from the Proacus book, alright, that's uploaded on one of the box folders. Okay, so I'm going to quantize all the coefficients. I'm going to quantize B scale and the A. We're using B minus 1 bits of precision because we know we always have one sign bit. Okay, it comes back with the integer number of bits and the decimal number of bits, and so we need 3 bits allocated to the integer part to represent a number like 7.2656, and then we have 6 bits allocated to the decimal part. Okay, so that's how that came out once you quantize those terms. All right, and so the way Q coefficient works is you get all the quantized bits in this matrix called BA hat. That's the notation he uses in Proacus. Okay, and so BA hat has both the B's. All right, so I'll highlight all the B's in green. Here are the B's. And it's also got the A's. So I'll highlight those in yellow. Here are the A's. Okay, so the next step in this code is to pull off the B's. All right, so we do that with MATLAB notation, and then we pull off the A's, and so we now have quantized filter coefficients. We can use that in the filter command a little bit later to do the frequency response of the quantized direct form 2 filter. Okay, so that takes care of the direct form 2 case where we have quantized coefficients. All right, so the next section of code, we want to convert the original. You can think of this as having infinite precision because it's floating point and you can get really good 32-bit or whatever precision. Okay, so with automatic scaling, by the way. So we know that the A and B vectors in their original form effectively are infinite precision. All right, so what we need to do now is convert that to the cascade form. You can do this in MATLAB, but I'm using the ProACUS code that does a direct form 2 to cascade conversion of the B's and the A's to the capital B zeros and A zeros with a scale factor B0. Okay, so B0 is a scale factor, and what you notice is you get the B's for the first section and the A's for the first section, the B's for the second section, the A's for the second section, and so forth and so on until you end up with 4 biquads. All right. Notice also, when you look at the scale of these, the scales of the B's and the A's are already comparable because the scale factor was taken care of in this B0 vector. All right, so we don't have to do that scaling step like we did with the previous filter. Okay, so at this point, we're ready to quantize. All right, so I'm going to quantize using the Q coefficient command. I quantize this array of B's and A's with B minus 1 quantization, and I can look at B hat and the number of integer bits and the number of decimal bits. Now notice the biggest numbers here in the original, you can see some 2's. All right, that's the biggest number, and so you only need 2 bits for the integer part, and that leaves you more bits for the decimal part when you use direct form 2. Okay. All right, so again, let me change the color here. This half of the BA hat matrix would give me the B's. So I'm pulling off the B's here, and then this half would be the A's. So I use some MATLAB notation to, if I wanted the B's, I use the first 3 columns. There's 4 rows and 3 columns, so that would give me the quantized B naught matrix. And to get the A's, I look at the last half of the B A hat matrix, and to get the A's. All right, so I've got quantized coefficients for the cascade form. All right, so our goal here is to compare the frequency response of the filters with quantized coefficients. So we can accomplish this by, direct form 2, we already have the coefficients. We can do the filter command and see what happens. All right, but to do the filter command with cascade second order sections, we need to convert that back to just a single A vector and B vector, and then we can use freq Z. All right, so that's what happens in the next step. We use the opposite direction. We go from cascade to direct. We factor in our scale factor B0, which we already calculated when we did the original conversion, and plug in their quantized cascade biquad coefficients. Okay, so that leaves us with B2 and A2. All right, and so from there we can calculate the frequency responses and make a comparison. Okay, so in the first frequency command, freq command, we have, I think I said filter command before when I was talking about frequency response. I meant freq. Okay, so we're going to use the freq command to do the filter response. So in the first one, these are the original unquantized coefficients. Okay, so that gives us, in some sense, the true frequency response. Okay, and then the first H2 filter is going to be with the quantized direct form 2 coefficients, and the second, the B2s and the A2s, remember those came from the quantized cascade coefficients. Alright, so we're looking at 3 frequency responses. The rest of this code is just setting up some plots. Alright, and so you can see the 3 different results. Okay, it's kind of hard to make the comparison when you see them stacked where they don't line up with each other, and so I put them all on the same scale with this command. Alright, and then I zoomed in to the interesting part of the frequency response. And so what you see here is there's very little difference between the original and the cascade coefficients. Those give you essentially the same frequency response. But when you only use 10 bits with direct form 2, you see some significant distortion with this red line. So it has too much ripple in the passband of that particular frequency response. Okay, so we'll explain why there's ripple in this response. In the ideal response with a Chebyshev filter, there's a certain amount of ripple that's actually allowed. Remember, for frequency responses, you generally want those to be flat. All right, so this has, when you use direct form 2, it has much worse ripple, all right, than what's allowed. So this would not be a good frequency response using those quantized coefficients. All right, so of course, if you allocated more bits, if you did this for 16 bits, then all these filter responses would probably line up pretty well, at least in the, when you start attenuating down in the hundreds of dB range, then you might see a difference then. But otherwise, things line up when you have enough precision. Okay, so there's a quick comparison of the filter types using quantized coefficients.